with those numbers, and here we won't be bothered with the numbers, but first one we formulate the equation of motions. Okay, so basically the statement of this problem is this. This is kind of the spinning. You can visualize this kind of the robot arm, okay, and kind of sweeping. And this is the spindle, and then this is kind of the loading. So the arm is made of three different segments of the bar. So individual by itself is a spring. So we have to find the spring constant first. So for this one, we can visualize this have an equivalent statement. Is this we have a spring 1, spring 2, and spring 3, and this is our loading. This is our the mass. For example, the mass here. So let me call it K1, K2, K3. Okay. And for this bar, we know that for the fundamental, if this is a Young's modulus, and if there's a cross-sectional area, okay, and if that has length L, and if this one, sorry, this is not spinning, I think this one is under axial loading, okay. So I think this bar we're kind of asking is the loading is applied in that direction, so this is our degree of freedom. Degree of freedom defined is in the axial directions, okay. So under this case, for this one, if we have a loading, something like this, again from mechanics material, we know that the deformations delta equal to FL over EA. So therefore, the KEQ for this case defined is the load divided by corresponding displacement, and that is equal to EA over L. So this is KEQ. So that means this is a K1. Basically, K1 is equal to EA over L for shaft number 1. So let me call this is shaft number 1, this is number 2, this is number 3. So here you simply plug in all the information for number 1. We are given the Young's modulus, we are given the length, okay, and where is the length? Length here, okay. And also we are given the cross-sectional, so for this case, this is the hollow shaft, the hollow bar. So hollow bar, you should be able to find the cross-section area. So basically here, you should be able to find this. So the same thing, K2 is EA, L, and for the number 2, etc. Okay? So in this way, in this case, we have is simply is KEQ, and with the mass. So what is KEQ? KEQ equal to K1 plus KQ plus K3. Am I right? Yeah. Just test it. Okay, that should be this one because they are in serial combinations, connections. Okay. So once you have this one, basically for this case, this is our degree of freedom xt. So the equation of motion is pretty straightforward. Plus KEQ x dot x equal to 0. So the natural frequencies from here you can see basically that is omega n equal to KEQ divided by n. So here we are given all the information, so that should be okay. So here this subject have the mass 10 pounds. So from here you can m basically equal to weight divided by gravity. What is the gravity unit for corresponding to pound? I think it's 360, 386 something. So basically this one will be 10 pounds by 386. Am I right?
32.
Huh?
32.2%.
Whatever. And I always, if I put this one, only remember the Newton kind of unit 10 or 9.8. This one always go to the Google. Okay, so this one they to you. So under this situation, you should be able to calculate M. KEQ is been the summation doing this one, and then using this formula, you have all the numbers ready to go. Okay, I think this is an example from our textbook.